Okay, so I'm going to try to make use of super crappy Zoom recording again here. We'll see how it goes. I've tried already twice. So because I got the new laptop, now I don't have the same recording software that I had before, and there's no way for me to get it. Super fun. Anyway, enough complaining. So let's see if I can get this garbage to work. Rightio then. So here we are. I'm sharing my screen now. Let's see how crappy this goes. Okay, so in this video, we're going to talk about logarithmic and exponential functions. And now Siri is listening to me. She's a moron. We're basically going to be talking about how they're inverses and how we can use that to our advantage, algebraically speaking, to solve logarithmic and exponential equations and to find inverse functions of the two. Okay, so without further ado, really quick, let's establish a few things about logarithms. And depending on how frustrated I get with this, I may not use Desmos at all to demonstrate this because I think you guys have a pretty good grasp of how transformations have been working this whole time, right? So before we do that, let me do something really quick. Oh, cool. I can't pause the recording without pausing my screen sharing. Okay, so I'm resuming the recording now because Zoom sucks and it doesn't let you multitask much, but what can I say? It's free, I guess. Okay, so anyway, so first let's look at a few things here. So all I'm gonna do, really, just click the link, bro. So all I'm gonna do is enter in an arbitrary logarithmic function. Okay, and just to illustrate my point, so when I say arbitrary, I'm going to go ahead and say arbitrary as in literally. So B can be anything, right? And in this case, I'm going to go ahead and just do base 2, right? So right now I'm doing log base 2, and let me up the contrast there. Zoom in a little bit more. Okay, so how is this working? How is this working exactly? Right? So how do we translate? Right? So if I take the same log base B, and it's going to use the same B in my slider there, and I want to translate either right or left. Well, we already have an idea how that's going to work. So if I do -5, right? Holy dog crap. I went 5 to the right. So we can see our x-intercept for the parent function of base 2, so log base 2 of x. Our intercept is always going to be at 1/0, right? But whenever I translated 5 to the right, of course, I went 5 to the right of 1, which is at 6, right? What about to the left? That's right, you guessed it. If I do +5, that puts me over 5 to the left at -4 as opposed to +1. Okay, so that's right and left. All we're doing is throwing into the parentheses here with a plus or a minus, right? Okay, so what about up or down? And I guess I'll go ahead and just -5, just leave it like that. Why not? Okay, so what if I wanted to shift 5 down? Well, you put a -5 on the outside of the parentheses. Oh, before I get ahead of myself. So when I was translating right or left, how did that affect my asymptote, right? So your horizontal shift is going to be indicative of where your asymptote lies, right? So that said, okay, that's important. That's a huge difference between log functions and exponential functions, right? Exponential functions, their asymptotes were according to their vertical shift, up or down, right? Logarithmic functions, the key difference there is in their shift right or left because they have vertical asymptotes, right? So the original parent function, we can see it has an asymptote here at x = 0 vertically, and the transformed one that shifted 5 to the right and 5 down now. Okay, that 5 shift to the right shows us that we have a vertical asymptote at x = 5. Okay, so that's how our asymptotes are affected, and we already know how to translate up and down. What about stretch or shrink? Oh, gee, I wonder if that changed. Yeah, no, it didn't. Okay, so if I want vertical stretch, and let's go ahead and get a good idea without the, sorry, I had to throw my phone again. Let's go ahead and get a good idea without the vertical shift, right? So we can clearly see I've been stretched vertically. Okay, well, what about shrunk vertically? Well, if I do 1/3 instead, right? If I do 1/3 instead, I have been vertically shrunk. And also take note, the asymptote didn't change. I'm still here at an asymptote of +5, x equals 5, okay? How can we reflect across the x or y axis? So reflecting across the x-axis, well, that's as simple as putting just a negative for the most part, right? So if I go ahead and undo that, okay, so I can see that I've been reflected across the x-axis. Okay, now what happens? What happens if I do this, right? Well, nothing happens if I do that because that makes it undefined. Now what happens if I do this? Ah, that's how we reflect across the y-axis. Okay, so reflection across the x-axis is a negative out here with our vertical stretch or shrink factor, right? Reflection across the y-axis is in here, inside, associated with the actual function of x. Okay, and that's going to look kind of familiar from our, what do you call it? Our cubic and, or not cubic, our cube root and our square root functions were a lot like this. Okay, so just a heads up there, that's how transformations are going to work. Okay, so how can we calculate f inverse if f of x is an exponential function? In other words, so looking at our first example here, so we're being asked to calculate f inverse of 1. There's f of x. So let's go ahead and do some of that math real quick. So to calculate inverses, obviously we have to flip. So I'm going to go ahead and call this x equals 10 to the f now, right? And I'm trying to get f by itself again. Okay, and in order to do that, I'm going to have to take log base 10 of both sides because that's the inverse of exponential base 10. So I'm just going to say log, and if there's no base here, remember that means we're log base 10. So log x is equal to log of 10 to the f. Okay, so log base 10, exponential base 10, they cancel. That leaves me with f inverse of x is equal to log base 10 of x. Okay, so this guy is the inverse of this guy. Okay, to put it as simply as we can. So inverses aren't really a new concept. Let's find G inverse. Okay, so same idea. I'm going to go ahead and flip G and X, right? So I'm going to say X is equal to e to the G power instead. And I'm going to do exactly like what I did over here, basically, right? So the inverse of base E is going to be, or the inverse of exponential base E is going to be log base E. And there's another name for that, right? So when I say log base E of some number X, what I'm really saying is natural log of X, okay? Ln means log base E. Okay, so that's an important FYI, and I don't remember if we went over that in the last lesson or not. I think I just established what the natural base was, right? So the log of the natural base is natural log. Okay, so I'm going to take natural log of both sides. Okay, these two undo one another. That leaves me with G inverse of X is equal to natural log of X, which makes sense, right? That's a lot like what we did here. Okay. Let's keep the party going. So H inverse. Okay, so this one's a little bit different. So I've got H inverse, or sorry, I've got H of X is equal to 2 times 4 to the X plus 1. Okay, so a little bit different. First, I'm going to have to divide, well, first I'm going to have to flip, right? So I'm going to say X equals 2 times 4 to the H plus 1. Okay, what I'm going to do next is divide by 2 on both sides. So now I've got X over 2 is equal to 4 to the H plus 1. Then I'm going to want to do log base 4 of both sides. Okay. Because I need to do the inverse of exponential base 4. The inverse of exponential base 4 is simply log base 4. And when I do that, log base 4, exponent base 4, they cancel. That leaves me with h plus 1 is equal to, and I can go ahead and split this if I want to, or I can leave it as is. I'm going to go ahead and split it just so that way we get used to seeing this kind of thing. So I've got log base 4 of x minus log base 4 of 2, right? And then I'm going to subtract 1 from both sides. So log base 4 of x minus log base 4 of 2 minus 1 equals h inverse of x, right? And again, this guy would be inverse to this guy. Okay, last example, yellow for this one. So we want m inverse, right? So this one's even uglier. But again, piece by piece, right? So x is equal to 1/2 times e to the m minus 3, all plus 1. Right? So I'm going to subtract 1. Okay, then I'm going to multiply by 2 on both sides. So I've got 2 times x minus 1 is equal to e to the m minus 3. Then I'm going to take the natural log of both sides. And notice that I'm using different kinds of parentheses so that way it doesn't get too messy. Oops. Just a minus. Okay, so I've got square brackets and I've also got curved brackets. That doesn't mean anything different. It's just so I don't get confused later. Okay, and then I'm going to add 3 to both sides. And I can go ahead and split this into 2 separate logarithms if I want. So I can go ahead and say that this is natural log of 2 plus natural log of x minus 1, and then the plus 3 equals m inverse of x. And that would be my final answer. And of course, I didn't have to do that last part. I didn't have to do this. Again, I'm just doing that to remind you that that is a thing. It does exist, right? Okay, so here we've got some other examples. And now we're going the other way, right? What if I want to find the inverse of a log function, right? So let's start with this first example. So I want to find f inverse. So I'm going to go ahead and flip. So I'm going to have x equals log of f. Okay, and again, there's no base here, so we automatically know it's assumed to be base 10. I'm going to go ahead and rewrite that as 10, just so that we can, just so we have the visual, right? And again, you know, it always helps me to draw these arrows like what you saw. So 10 to the x equals our f. So f inverse of x is equal to 10 to the x. And that makes sense, right? So log base 10 of x is inverse to exponential base 10 of x. Okay, next example. So we want to find g inverse. So we're going to say x equals natural log of g, right? And remember, so natural log is log base e, okay? So what I'm going to do is do exponential base e to undo both of these guys. So basically, I'm just going to say this. E to the x is equal to e to the natural log of g, right? Exponential base e, natural log e, they undo one another. They're inverses. So g inverse of x is therefore equal to e of x, or e to the x. Okay, another way to look at that is the same way as how I did the last problem. If this way was a little bit confusing. So if you want and you need that visual still, just rewrite natural log as log base e, right? And just draw the arrows. So e to the x equals g, and we know that's going to be g inverse, right? And we get the exact same answer. Okay, whatever works for you, whatever helps your brain, right? Okay, so now let's find h inverse. Okay, so x equals 2 times log base 3 of h. So we're trying to find h inverse now. Okay, so we're going to divide by 2 on both sides. X over 2 equals log base 3 of h. Okay, I'm going to go ahead and draw the arrow. Okay, so that means I've got 3 to the x over 2 is equal to h inverse of x. Or we could have done that in a purely algebraic sense, right? It's a little less visual, but some of you guys have a more linear brain that way. So divide by 2, we're going to keep that step the same, right? But we can also say that the inverse of log base 3 is exponential base 3. So I can say exponential base 3 or 3 to the log base 3 of h. Those are inverses. What I do to one side, I do to the other. It is an equation, right? And that leaves me with the exact same answer of 3 to the x over 2 is equal to h inverse of x. Still works out the same way. Okay, so now let's find m inverse. So x is equal to 1/2 times the natural log of m minus 2. Remember, we're flipping, all plus 1. So we're going to go ahead and subtract 1 from both sides. Okay, then we're going to multiply by 2 on both sides. Okay, then we're going to go ahead and do the exponential base of, so the exponential natural base of both sides of the equation. So if I'm doing exponential base e to both sides of the equation, so natural base, exponential natural base, right? They undo one another. Okay, and that's going to leave me with e to the 2 times x minus 1 is equal to m minus 2. Okay, and I'll redo it with a more visual representation here in a second. Okay, add 2 to both sides. And that's going to be my m inverse of x. Okay, or if I use the more visual method with the whole drawing the arrows thing. So back up, back up, back up, back up. So that's going to take me to this point. I think I went back too far. Yeah, still need to multiply by 2. So none of the first steps are going to change. Okay, so this is where it's going to be a little bit different. Whoa, what's the matter with me? So instead of saying natural log, I'm going to just say log base e, so that way I can draw my arrows. Right, so e to the 2 times x minus 1 is equal to m minus 2. E to the 2 times x minus 1 is equal to the m minus 2. And we're going to arrive at the exact same conclusion. Okay, so same idea. However your brain likes to look at these, that's completely up to you. So now that we've seen how we can do some algebraic messery with these and how we can manipulate these functions and equations, we're going to put that to good use here. So the implications of what we did in EQ2 and 3 is that we can use these inverses to solve equations, right? So I'll start with yellow, why not? So I've got 4 to the x minus 5 is equal to 16, right? I'm just going to add 5 to both sides. I'm solving for x right now, if you haven't figured that out. Okay, so add 5 to both sides. Okay, then I'm going to do log base 4 of both sides. Okay, and this isn't going to come out nice and cute. I'm going to have to throw this into a calculator, right? So I'm going to do, let's see, log, or actually, I might as well type this for you in Desmos. So let me copy my link over here. Let's see if it'll let me. I think I can just copy it like this. Let's see if this works. Ah, okay. So I'm just going to use Desmos here. So I'm going to say log base 4 of 21. And yeah, there it is. It gives me my decimal estimate. So 2.196. That's approximately, x is approximately 2.196. Okay, and that would be my final answer. So solving these kinds of equations is so easy. Okay, so I've got 1/3 to the 2x equals 1/9 to the 4 minus x. What I'm going to want to go ahead and do here is do, I'll go ahead and do log base 1/3 and see how that plays out. So I'm going to do log base 1/3 to both sides. Well, I guess I don't need to show that step anymore. You've already seen me do it a million times. So that's just going to be 2x is equal to, so now we've got log base 1/3 of 1/9 all raised to the 4 minus x, right? So this is where it's going to get a little bit tricky and complicated, right? So I have to think separately. So 1/3 to what power gives me 1/9, right? So we're not worried about this 4 minus x just yet. Okay, all I'm worried about is canceling here, right? So if I come and look at this separately over here, so log base 1/3 of 1/9. Okay, so 1/3 to the second power is going to give me 1/9. Is that true or false? Well, 1/3 times itself does in fact give me 1/9. So my answer to that logarithm would be 2. Okay, so I can do, just to kind of illustrate what it is that's happening here. So log base 1/3. So what this really is 1/3 squared. And then laws of exponents tells us, right, that this 4 minus x would be up here. Okay, so it'd be 2 times 4 minus x. Okay, so and the reason for that, so if I've got 1/9 all being raised to the 4 minus x, this is why it's so important to understand the laws of exponents. Okay, so this is the same thing as 1/3 squared being raised to the 4 minus x, right? And what do we do with the power to power rule, right? We multiply those. So this would be 1/3 to the 8 minus 2x. Or you could just leave it undistributed, which is what I'm going to do just to kind of prove a point. Okay, anyway, so log base 1/3, exponential base 1/3, they cancel. That leaves me with just 2x is equal to 2, and you know what? I will go ahead and distribute it. So 8 minus 2x, right? So that's going to give me 4x is equal to 8, x therefore equals 2. Okay, and you can always check your work, right? So if I say x equals 2, well, I better darn make sure that this actually works when I plug this back in. So 2 times 2, well, that's going to give me 4, right? And 1/3 to the 4th power. Brain fart here. 3 raised to the 4th power. So that would be 1/81, right? This guy here would be equal to 1/81. And then over here on this side, this would be 4 minus 2, which gives me 2. So this would be 1/9 squared, which is also 1/81. So those two are equal. So our answer x equals 2 checks out. Okay, just like any equation, you can always do that. Okay, so that one was complicated. That one is on your homework, just FYI. So hope you paid attention on that one. Okay, number 3, 8 to the x equals 100. Easy peasy, just do log base 8 of both sides. Okay, we can just throw that in the calculator. So we can go ahead and say that we've got log 100. And I'm using, well, I'll go ahead and show you on Desmos. And you can get out of the habit of using my graphing calculator. So log base, whoops, not B, what's wrong? Base 8 of 100. So 2.215 thereabout. I don't know why it's saving all of these. So 2.215. Okay, and number 4, our last example. Okay, so all we're going to do is divide by 3 on both sides. Okay, so that's going to give me e to the x plus 2 is equal to 29. Then we're going to do natural log of both sides. X plus 2 equals natural log of 29. Subtract by 2 on both sides. So natural log 29 minus 2. Okay, so natural log 29 minus 2. That's going to give me approximately 1.367. Okay, so I mean, these are the algebra behind these is not very difficult. So now we're going the other way around, right? And we can do this as easily as just drawing the arrows, or we can use exponential bases, however you want to think about it. This first one, I'm going to just draw the arrows. Okay, so 3 to the 4th is equal to 4x plus 1. 3 to the 4th, of course, is 81. Subtract 1 from both sides. 80 equals 4x. X is therefore 20. All right, let's look at the next one. So I'm not going to do this one with the arrows. What I am going to do is go ahead and do the, so I'm going to do a few things. So right here, I can go ahead and use the quotient law. Okay, and on second thought, no, I'm not, because that's going to get really ugly if I use the quotient law. I'm going to go ahead and just raise both sides to the e. Okay, and what that's going to do for me is when I have e to the ln of x plus 4 minus ln x minus 4 equals e to the 4th, right? I'm going to be left with, and I need to be careful here. So hold on 1 second. No, I was wrong. The book does suck that bad. Okay, so I'm going to have to do this the hard way, or the way that I was not thinking that they would throw at you. But it's not so bad. You need to see this because the very next lesson, well, the very next section is going to be over these kinds of equations. So we need to at least see one example first. Okay, so I do need to go ahead and simplify this guy. Okay, so we're going to go ahead and use the quotient law here. So what I'm really going to have is x plus 4, the natural log of x plus 4 over x minus 4, like so, is equal to 4. Then I'm going to do, so to undo this, quote unquote, I need to do exponential natural base, right? And that's going to leave me with x plus 4 over x minus 4 is equal to e to the 4th power. Okay, so what I'm going to have to do now is put e to the 4th over 1, and I can go ahead and cross multiply here. So I'm going to have x plus 4 is equal to e to the 4th times x minus 4. And this is going to get a little bit ugly. It won't be that bad. So I'm going to have e to the 4th times x minus 4 e to the 4th. And I've still got the x plus 4 sitting over here. So I want to get all my x's on one side and all my constants on the other. So I'm going to have x minus e to the 4th x is going to be equal to negative 4 minus 4 e to the 4th. Then I'm going to go ahead and combine like terms. So e to the 4th, and I'll go ahead and use my decimal. Well, no, I won't because I didn't copy the link over. So e raised to the 4th power is approximately 54.598. So if I've got 1 minus that, I'm going to have approximately negative 53.598x, right? Because this is 1x and I'm taking away approximately 54.598x, right? So that leaves me with a negative here. And then over here, this is going to end up with, so negative 4 minus 4 times e raised to the 4th. That's going to be approximately negative 222.393. Okay, then we're going to divide both sides by this negative 53.598. You do to one side, you do the other. And I'm using a graphing calculator, so my answer is going to be pretty dang accurate. And I get approximately 4.149. Okay, so that is pretty gnarly. Okay, but this one is in your homework. But I mean, I've pretty much done it for you here, so no big deal. Okay, so here we see one that's kind of similar, except we're going to use the product law here. Okay, so we're going to have log base 2 of 2x times x minus 3. And all of that is equal to 3. Then we're going to do exponential base 2 to undo the log base 2. So that's going to leave me with 2x squared minus 6x is equal to 8, because that's going to be 2 to the 3rd here, gives me the 8, right? And then we're going to have a handy dandy quadratic. So 2x squared minus 6x minus 8 equals 0. Then we can go ahead and, so factoring is not going to work. Because I'm going to have, oh, yeah, it is. So AC grouping is going to tell us that we're going to have AC equals negative 16. Okay, so I can go ahead and use negative 8, positive 2. Okay, so 2x squared minus 8x plus 2x minus 8 equals 0. Okay, then I can go ahead and group and factor. Okay, so over here, all I have is an x. That leaves me with x minus 8. Over here is just a plus 1 that I'm going to factor out. That leaves me with 2x minus 8 still. Whoops, whoops, whoops. Got the 2 over here. Okay, and factor again. My GCF is going to be 2x minus 8. And that leaves me with x plus 1. Okay, so my two solutions are going to be, so obviously the first one is going to be negative 1. Okay, and our next one is going to be, so that's going to be 8 over 2, that's going to be 4. Okay, so those would be my two solutions. Now, this is where we need to see something. Okay, there do exist extraneous solutions to logarithmic functions, right? And there's two ways to tell, but the quickest way to tell is to just plug them back in and see if they work. So if you ever get more than one solution for a logarithm, for a logarithmic equation rather, okay, you always want to go back and see which one is going to be extraneous. And I can go ahead and tell you, so if we just work smart here, right? So 2 times negative 1, right? That's what I've got here, 2 times x. If I'm looking at this first solution, that's going to give me negative 2. Well, 2, there's no exponent you can raise positive 2 to get negative 2. There's no exponent that's going to give you negative 2 with a base of 2. It's just not possible, right? So that right off the bat tells me that this negative 1 is extraneous. Okay, and that of course is not going to happen if we plug the 4 in, right? So if I look at the 4 instead, so 2 times 4, well, that's going to be 8. So 2 to what power is going to give you 8? So this becomes just 3 plus, and then 4 minus 1. So this is just going to be 0. And 3, of course, plus 0 does in fact give you 3. Okay, so always be careful of those things. And now what we're going to be asked to do is to find a final law of logarithms, okay, namely the base change identity. Okay, so we'll go ahead and look at that right now. So log base 9 of 729. So 9 to what power? 9 to what power gives us 729? Well, the answer there is going to be 9 to the third power. So log base 9 of 729 is equal to 3 because 9 to the third power is 729. Okay. Log base 5 of 125. Well, that also is going to be 3 because 5 to the third power gives us 125. Okay, so now we see some uglier ones, right? So now we've got log base 10 over log base 9, right? So, well, okay, sorry. Log base 10 of 729 over log base 10 of 9. So anyway, when we throw that in the calculator, so if I just hit log 729, that's going to give me approximately 2.863. And log base 10 of 9, so just log of 9, 0.954. Okay, when you divide those two numbers, you get precisely, holy dog crap, 3. Okay, that looks familiar, right? And then look at these two numbers too. Right, so we're establishing a pattern here. Okay, same thing over here. So natural log of 125 over natural log of 5. So natural log of 125, that's going to be 4.828 thereabouts over natural log of 5, 1.609. And when you divide those two numbers, you get precisely, holy dog crap, 3 again. What is the pattern, you may be wondering? Hopefully you're not wondering too hard about it. So 125 over 5, 125 base 5, 729 over 9, 729 base 9. Here is the identity. Okay, if I've got log base y of some number x, that is equal to log of some base b of x over log of the same base b of y. Okay, so here in both instances, top and bottom, we had log base 10 here, right? Log base 10 here, log base 10 here. Okay, here, top and bottom, we had log base e and e. As long as the bases are the same, this identity always holds true. This is our change base identity or base change identity. And that's the last law of logarithms we're going to learn off the top of my head. Okay, so that is about it for this video. Like always, send me an email if you have any questions. Otherwise, until next time, goodbye.